Okay, and the next presentation is by David Verhoeven, and it's an economic optimal control model of land subsidence. David, your floor is yours.
Yeah, thank you, Gilles. So I will talk a bit about the economics of land subsidence and a model that I've been working on with my two co-authors. We are all from the Wageningen University, the group of environmental economics and natural resources. So that's why I, in the first session, raised my hand that I was an economist. I'm not fully by training, but since no one else was, I thought I'd raise my hand. This research is also part of the LOS project that Bernardine just taught about. So on the economics of soil subsidence, of course, as we already heard today, and as you all know, subsidence is exacerbated by anthropogenic drivers like urbanization, agricultural intensification, energy extraction. In other words, economic activity. And countering subsidence also always has an influence on economic activity, and that interaction needs to be understood and can also be used to come up with a good policy. So in the Netherlands, for example, but in other soft soil delta regions as well, to allow economic activities such as agriculture, soils are drained, speeding up subsidence, which requires further subsidence to keep economic activity, leading to this continuous cycle. I think Gilles also already included this nice figure that depicts that in his presentation. Which also leads to depletion of the upper soil layer that gives this economic activity. To stop that cycle, we would have to, for example, raise groundwater levels, but that would be at the cost of current productivity gains. So there is this intertemporal trade-off between current productivity gains of continuously lowering groundwater levels and the cost of subsidence for the future and also for future generations, which requires long-term and efficient policy decisions. So in the Dutch situation, which is where we focus on in our paper, we have 9% of total land area, which is low-lying peat, which is mainly used for intensive agriculture, particularly dairy farming. So this is the case that we focus on in our model, but it can be applied to other types of land uses. And there you have this continuous cycle over the past centuries, responsible for 2 to 3% of yearly greenhouse gas emissions and increasing management costs to keep this cycle going. So because of that, there is now also a policy discussion. The business as usual scenario used to be that we go down this path of continuous groundwater lowering to keep pace with subsidence. But now the policy discussion is tending towards more to higher water levels to avoid damages and costs, but maybe also to save the peat for future generations. I don't know whether that is much discussed in the policy documents, but we argue in this paper that it should. But that comes at the cost of current economic activity, without a doubt. So usually when we talk about these economic evaluations, we talk about possible future scenarios. I think these three types of scenarios we've already heard today. The business as usual case, the case where we slow down by fixating groundwater levels and we go slowly down towards that level, or actively heightening groundwater levels to stop subsidence. So what we typically do is then evaluate the effects of such scenarios. What we try to do here is, from the dynamics of subsidence in relation to economics, to economic elements, come up with, and that's what we are interested in as economists, what is an efficient use of our resource. So what we try to do in this paper is integrate the dynamics of land subsidence and groundwater management into a bioeconomic model to derive socially optimal paths, so a social optimal policy for over a long period of time. And for that, we use a technique called optimal control theory, which is basically a mathematical framework to find the best control actions for a dynamic system, subject to constraints and objectives. So we have an objective that we want to reach, something that needs to be maximized or minimized, and what kind of control actions do we need to take to reach that objective, subject to constraints. Optimal control theory is widely used in many disciplines, but in economic natural resource problems, it's used to decide how to manage a scarce resource efficiently over time. And from this technique, we can derive optimal policies analytically, but also with numerical simulations. We do both in the paper, which guides the development of efficient long-term resource management strategies. And for that, we need to model the dynamics between a state variables and stock control variables. And in this case, the state variable is this peat soil, or the soft soil, that is our resource. And our control variable is the groundwater regulation that we can apply, which looks very schematically a bit like this. So for mathematical reasons, we measure the height of the groundwater level from like a 0 point, which gives the groundwater depth we indicate with an R. I'm going to skip this for time. So so what is fundamentally different, that's for the with existing economic evaluations, is that you predefine, instead of predefining a set of scenarios that you evaluate, we build a model that gives as an output the optimal policy. So that's the fundamental difference. So that's what we have. So we only need as input a few local physical and production parameters, economic parameters, a discount rate, because we are talking about dynamic systems, and some soil measures. Then we have the optimal control model that models these dynamics between soil subsidence and between economic elements. We have included here only agricultural revenues and water management costs, but we are working on extending this. And as an output, we get an optimal policy, basically the total economic value for such a policy, a final time horizon, and welfare gains. With respect to a benchmark, I will come back to that later. So first we have to define an objective, which is basically to maximize the total economic value over a period of time from a plot of land. And that there we include the agricultural net revenues and the cost of water management up to a end horizon, end of the time horizon. So then we model the dynamics. We have an equation for the subsidence. We have an equation for the yields, which is related to both our state variable and our control variable, because of course with wetter conditions we have less yields, and the other way around, up to a certain point we can increase our revenues by further drainage until it becomes too dry. And we have cost of water management, which increase in depth, in absolute depth. We can play around with that as well. And we have to define what our end time is. So we define here when basically our end time is when our soil doesn't have economic value anymore. So that is either when further subsidence is too costly, because maintaining costs become too high, or when we have reached the water level below, when the water level reaches below the peat, because then we can't do anything about subsidence anymore with the groundwater level, with our control variable. And then we have a few scenarios that what is below then? Is there a layer below that still has some economic value that we can use, or not at all? And we work around with it. I can imagine that this sounds very highly stylized, and we have opportunity for more soil context in extensions, but what we try to do here is to have a simple as possible model that is still analytically tractable, that we can give economic interpretation to that still reflects the core dynamics of the system, right? And we can extend that, but then it becomes much more difficult. We compare that to a benchmark policy. So from the model, we get the optimal policy, and we compare it to benchmark policy, which we call myopia, which is basically a policy where we maximize profits at each point in time separately, without considering any consequences for the future of our decision now. So we call that a myopic or a short-sighted policy benchmark. And in economic terms, we equate marginal costs with marginal benefits at each point in time. And in practice, we show this mathematically, that this is equivalent to water level indexation, basically the business as usual scenario for the Netherlands, where we lower the groundwater level in keeping with subsidence at a certain root zone. So this is not considering future costs. So we do a baseline calibration to assign parameter values based on subsidence relations that also are used in other models, agricultural revenues, water management costs from previous social cost benefit analysis. There are a lot of assumptions there as well in those research, but it's the best parameters that we have for this. And that gives optimal paths for subsidence, where we compare. So the bottom, the dotted lines are always the groundwater level, and the straight lines are always the soil thickness. So with thick peat, we already see, so you can see the lowest line is the myopic groundwater level, and this line is the optimal groundwater level. So you see it's higher throughout time, which means we have lower subsidence, and we extend the period over which we can exploit basically this peat soil. So we save more for future generations. This is optimal compared to the business as usual scenario. We worked that out for different scenarios as well, but this might be more indicative. So we have the benchmark policy, and we have the optimal policy here. When we assume that we have linear costs in depth. So as we go down, our costs increase, but this is linear. So the marginal cost of every lowering is the same. And then we get that we have a groundwater depth which is lower, but surprisingly increasing over time. So it's actually optimal in this scenario, or in this with these assumptions to heighten water levels now compared to the benchmark, but reduce that effect over time. Now, for these very long time horizons, you could argue that this is not a good assumption, that these costs actually, when we go down further and further over time, that these marginal costs actually increase because we need more infrastructure, we need larger dikes, we need to pump the water higher up. So there is actually an exponential element to these costs. And if we assume that, then we see that the benchmark policy has a much shorter time horizon, of course, because it's becoming much too expensive much more quickly. And in the optimal policy, we have a much lower groundwater level over time. And we have much higher welfare gains from adopting an optimal policy compared to the benchmark. So we can play around with this to see the welfare gains compared to how much peat we have in the initial situation. That's this. Of course, when we have, we can play around with the assumption of the parameters that we use in the model. So if we have slower subsidence, our welfare gains from adopting an optimal policy compared to the benchmark are higher. And if we apply a lower discount rate, we also have higher welfare gains from basically extending the period, slowing down subsidence, which is logical because a lower discount rate means we have more more care for the future and for future generations. So, in conclusion, we show in our paper that water level indexation is a myopic policy, so it does not consider future generations. It is socially optimal to heighten water levels now to save resources for the future, for future generations, even without considering external damage costs, because remember, we didn't include that yet in our paper. So this is important to remember. So just the saving for future generations is already a sufficient rationale to heighten groundwater levels now. And ignoring this dynamic efficiency leads to substantial welfare losses. And this finding supports the current policy trends and the policy decisions. The most important next step that we are currently working on is to add greenhouse gas emissions to the objective function as a cost function of subsidence, based on the interaction with the water table. Of course, we not only want to include CO2, but also methane emissions, which can be a bit of a counterbalancing factor with very high water tables. So when we need to take into account greenhouse gas emissions, we need to also take into account the trade-offs that might be there, which also allows us to basically calculate the applicability of underwater drainage and infiltration drainage, because we can calculate, because this basically reduces emissions while maintaining agricultural outputs, but it comes at an investment cost. So that is something that we can include in the model as well. Now the model is deterministic. We can add some uncertainty, as the groundwater level, of course, cannot be fully controlled. There are some fluctuations that might exaggerate or subsidence that we cannot control. And if we do that, we are able to have a spatial application based on soil and land use data for the Netherlands of this model. So that's it. Thank you very much.
Thank you, Davy. Any questions for Davy?
Thank you for your interesting presentation. I have a question. The agriculture, it is the, I guess it's about the cows and so on. Like paludiculture is not involved, I guess.
No, so no, indeed. So we assume we don't allow for land use change or other agricultural activities, but we could. So, for example, if paludiculture becomes economically viable, we can add that as a parameter of economic output when we have very low groundwater levels, and see what that does to the model. But then we have to, with all these kind of extensions, we have to resort to numerical simulations, because it becomes the results become intractable. So we want to single out this generational trade-off with this model, and then we can add modules basically to that.
Yeah. Yeah, and for the rest, I think it's interesting to add the greenhouse gas emissions. Yeah. Then the outcomes will probably change a bit. Yeah. Hopefully. Okay, I think that's it. Yeah.
Hey, any further questions, Saskia? Yeah.
Yes, Davy, thank you for an interesting talk. I was thinking about our previous speaker, and how do you engage with your stakeholders and try to go beyond your research outputs and make impact? How do you do that now, or plan to do that?
Yeah, that's
in your research.
That's a good question. I think that's that comes into play when we. I hear this alarm going. So for this is mostly, of course, this first paper is a theoretical exercise, largely, to indicate the policy relevance. But of course, we want to use this to also go more towards cost-benefit analysis of concrete policies that are put forward. And there, I think this policy, this stakeholder engagement of what is actually possible in the field, of course, because that is a bit ignored here. What is actually possible to implement over such a long period of time, that becomes very important then. Yeah.
Okay, sorry. Thank you very much for your presentation. A big round of applause for Davy, please.